All right, welcome guys to our second snow day. So if you're watching this, this is the introductory video for section 6K. If you're watching this video, I'm assuming you are solid, at least for the most part, on the sections preceding this. So section 6J, which introduced you guys to conditional probability and a little more of the set notation we're using. So hopefully you are comfortable with the set notation and how we're using that, because it's going to start to get a little more complicated here. And to start you guys off with 6K, I'm going to cover a topic that we talked about earlier this week and even last week, and that's something called mutually exclusive events. And I wanted to go back to this one because this and our new topic for 6K are two phrases that kind of get intermixed, and they're most definitely not the same thing. So you have to kind of get used to using these two and understanding the difference, like how they are very different. They do not mean the same thing. And so when we talk about mutually exclusive events are just two events that cannot or do not occur at the same time. And one of the ways we say that using set notation is we have the probability of A intersecting B is equal to, basically it's zero. This little thing right here, if you're not comfortable with that, that's what's called null set. And I wouldn't stress too much about this, just knowing when you see that, that's basically our way of saying that there is no answer, there is no intersection. And that's what mutually exclusive events are, is there is no overlap. They do not occur at the same time. Now, how does that show up, for example, in a Venn diagram? Because that is one of the things that I wanted you guys to get out of section 6J, was the ability to use equations and Venn diagrams kind of in tandem with each other. So using the equations, but then if you get stuck, kind of transitioning over to Venn diagrams and using them not as a crutch, but as a guide. And so sometimes you can do problems or calculate things without a Venn diagram, but sometimes it really is necessary to wrap your brain around what the probabilities are and what's actually happening in a given scenario. So in this particular instance, though, if you have mutually exclusive events, they do not have an intersection. So there is no overlap between event A and event B occurring. So in this particular instance, if you have a drawing like this in your Venn diagram, you say that A and B are mutually exclusive. And I think I introduced this to you guys before, where we talked about mutually exclusive being A and A complement, or A prime, where A is everything inside of this particular bubble, and then A complement is everything outside, but still within the universal set of all the possible outcomes. Same thing with B and B complement, or B prime. B is everything in here, and then B complement is everything on the outside. So B and B complement are mutually exclusive, and A complement are mutually exclusive. But now we have another term. And again, these mess people up. They use them incorrectly. They use one when they should be using the other one. We have what are called independent events. Independent events are just two events. They either could or do not occur at the same time, but the probability of one occurring has no impact on the probability of the other happening. So again, mutually exclusive cannot happen at the same time. Independent just means they could or could not happen at the same time, but the probabilities are not impacted. A very, very, very simple example of that is, what if I give you two events? Event A is the probability of flipping a fair coin and getting a fair two-sided coin and getting ahead. And event B is rolling a standard six-sided dice and getting a 1. So those two things, if you did them at the same time, you could flip a coin and roll a dice, and those events could occur at the same time, but the probability of one is not going to impact the probability of the other. And don't try to create situations where, oh, well, what if I flip the coin and roll the dice and the dice hits the coin and causes it to flip? The probability of that happening is so small, it has no impact on that. So we're not going to get into all those weird situations where something like that could happen. We are just saying that if you flip a coin and roll a dice, the probability of getting ahead is not impacted by the probability of you getting a 1 on the dice, and vice versa. And so if we write those, the probability of A, so the probability of getting ahead is 1/2, or 0.5, and the probability of rolling that standard six-sided dice and getting a 1 is 1/6. And I know sometimes we use decimals, but the fractions are fine. And so these two events are independent because the flip and the dice have no impact on each other, the probability of them occurring. So what we're going to do is transition over into how these impact the equations that you guys have learned already. Now, the first equation I gave you, which I did not write up top here, was the probability of A union B. So that was A or B occurring. And we said that the probability of that happening is the probability of A plus the probability of B. But then if there's any overlap between A and B, you're counting that overlap, that intersection, twice. So you have to subtract the probability of those two intersecting each other. Again, in a Venn diagram, that intersection is just this little part right here. So if you just do A plus B, you're counting that middle part twice. Okay. The second formula, and these are the two big ones you have to have memorized. The second big one is the formula you guys did from 6J. Again, this is 6K, so I'm assuming you guys have already worked through 6J, and I didn't really have a lot of people asking questions, so hopefully we're okay with that one. This is conditional probability. So this says the probability of A given B. So we're saying that event B has already occurred. What's now the probability of A occurring? And the formula I gave you guys was the probability of A given B is the probability of A intersecting B. So basically the probability of both of those events occurring at the same time divided by the probability of the given. And that is the formula for conditional probability. Well, what I'm going to do now is I'm going to take that equation and I'm going to kind of manipulate it a little bit. The same way we were able to manipulate this equation up top, where you were able to take the intersection and since it's subtraction, you can move it over here and take this guy and move it over there. Those were kind of interchangeable. We can move stuff around just like you would in any equation going back all the way to algebra 1. So what I'm going to do is I'm going to take that equation above and I'm simply, and let's get rid of a lot of this junk here. I'm simply going to multiply the probability of B over to the side. So that gives me the probability of A intersecting B is equal to the probability of A given B times the probability of B. But now think about this in terms of what we talked about with independent events. We said that independent events do not impact each other, the probability. So if I ask you the probability of A given B, well, if A and B are independent events, then that means the probability of A given B shouldn't be any different than the probability of A. Think about that for a second. So the probability of A given B, if I give you B, if they're independent, B has no impact on A occurring. So what we're going to do is we're going to take that equation and we're simply going to write it as the probability of A. Now, again, this only works for independent events. So the probability of A given B, if they are independent, is just the probability of A, because B has no impact on A. Well, then we end up with a very simple equation that you've actually learned. I would bet you used this back in middle school. So the probability of A intersecting B is equal to the probability of A times the probability of B. And they actually call this the multiplication property. So I'll write multiplication property here. And it only works for independent events. So the probability of A has no impact on B. So they call this the multiplication property for independent events. So I'll pause for a second. If you guys need to pause the video to write that down, I would most definitely write some of that in your notes. So the multiplication property for independent events is the probability of A intersecting B is equal to the probability of A times the probability of B. So if we go back to our problem right here, and I ask you guys, well, what's the probability that both of these events occur? So basically, what's the probability that I flip the coin and get a head, and I roll the dice and get a 1? Well, you guys did this way back in middle school when you did independent events. You just didn't call them that. The probability of getting a head is 1/2. And the probability of getting a 1 on the dice is 1/6. And you guys were just allowed to multiply those together and say, well, the probability of both of them occurring is 1/12. So you did this not even realizing you were using this new multiplication property and you had two independent events. And I'll say one more time, I know I've stressed this a lot. The only way this works, though, is that the two events you have are independent. They do not interact with each other. The probability of one occurring does not impact the probability of another occurring. So some extensions we have for that. First one here is the probability of A given B is just the probability of A. Because if they're independent, B has no bearing on A. Therefore, the probability of A given B is equal to the probability of A. Same thing here. The probability of A given B prime. Well, anything related to B, if I say the probability of A, anything related to B is irrelevant because it doesn't have any impact. So the probability of A given B complement is just probability of A. Same thing here. What if I switch it up and say the probability of A complement given B? Well, again, anything associated with A is not impacted by anything associated with B. So keep that in mind when you have these independent events, that A and A prime are related to each other. And if they're independent, these have no impact on the probability of the others. And then an extension of that we might do periodically is what happens if you have 3 events. We're not going to dive into all the different possibilities because I think you guys remember from Venn diagrams that things can get a little complicated when you start getting 3 overlapping events like that. So just know that if you have 3 independent events, the probability of all 3 of them occurring at the same time is just the probability of A times the probability of B times the probability of C. So here's a visual example, if you guys want, for the A and B event we talked about. So the probability of flipping a coin and getting a head, and the probability of rolling a dice and getting a 1. So if we look at this, the probability of flipping a coin and getting a head would take care of all these 6 right here. So those are the 6 outcomes out of the total 12. The probability of rolling the dice and getting a 1 would be these. And so the probability of both of those occurring at the same time, since they are independent events, would be 1/12. And if you want for practice, you can pause the video and try to fill in the Venn diagram. I think that would be good practice. I'll wait about 5 or 10 seconds here to give you a chance to pause the video. You should be able to, based on what we've done, fill in all the missing pieces of information over here in the Venn diagram. So why don't you go ahead and try that? Okay, if you didn't pause the video, that's fine. So we said that the probability of them occurring at the same time is 1/12. So we know that's the inner part right here. The probability of getting a head is 1/2. Well, 1/2 is also 6/12. And since heads is this circle, that takes care of all these. Well, one of those 6 is in here, which leaves you with 5/12 out here. Same thing on the back end over here. The probability of getting a 1 is 1/6. I should do that in a different color. Is 1/6, which is this area right here. And so 1/6 is also equal to 2/12. And since one of those 2/12 is in here, we know that you only have 1/12 left over here. And then if we do 5 plus 1 plus 1, we get 7, which leaves us with 5/12 on the outside, which makes sense according to our diagram. Because if you look, we have 5/12 here, but you also have 1, 2, 3, 4, 5 outcomes right there that do not have either a head or a 1. All right, so let's look at an example that you will see in your homework, and we're getting close to the end, so I appreciate you guys being patient. This is independent events, so we have 2 events. Probability, or event A, is Mr. Erbank yells at someone while driving to school, and the probability of that occurring is 0.15. If it's during the winter, it's probably higher because winter drivers annoy me. And then B, the probability, event B, is it rains on a given day in London. If you guys don't know, it's very, very common for it to rain in England. So the probability on any given day that it rains in London is 0.56. And I ask you, are those 2 events independent? Or could you prove they're independent? Now, common sense would tell you that, well, Mr. Erbank yelling at someone while driving to school doesn't have any impact on whether it rains in London. But according to the probabilities, if I say the probability of A given B is equal to the probability of A. Now, we're assuming if these are independent events, which they are, and how do I know? Because I'm telling you that they are independent. Now, what if I didn't tell you they're independent? You guys have to prove it. But that means that the probability of A given B, we said for independent events, the given doesn't mean anything. So the probability of A given B is equal to the probability of A, which is 0.15. The probability of B given A, so that's the probability of it raining in London, given that Mr. Erbank yelled at someone on a given day. Again, independent events, which means this given does not have any impact on it. Therefore, the probability of B given A is just the probability of B, which is 0.56. Therefore, since they are independent events, we can say, what's the probability of these two things occurring at the same time? You can simply just multiply those two probabilities together. And so the probability of Mr. Urbank yelling at someone while he's driving to school and it raining in London is 0.084. So roughly 8.4%. Again, this only works because they are independent events. All right, last problem, and then that is it for today. The video, I'll try to keep it a little shorter next time we do this. So independent events, A and B, so they're telling you they're independent, and they're saying the probability of B is 0.4, and the probability of A union B is 0.75. What I would like for you guys to do, again, is pause the video, try to solve this one on your own, and what they want to know is, what is the probability of A, and then what is the probability of A intersecting B complement? Remember, equations and Venn diagrams, you can use them together. Sometimes one is easier than the other. So go ahead and pause it, try to solve this, and then if you don't pause, I'll wait about 5-10 seconds and then go through the answer. All right, if you didn't pause or you're back from pausing, let's go through. So they said the probability of B is 0.4. The probability of A union B is this. And they want us to find out what the probabilities are. So now we kind of have a situation here where how do you find out what the probability of A is? It doesn't seem like there's enough information. We have a couple formulas available to us. Now, hopefully everyone can see that this is not a conditional probability problem. There are no givens here. But we do have the formula that says the probability of A union B is equal to the probability of A plus the probability of B, that's really sloppy, minus the probability of A intersecting B. Remember that this was the main formula I told you guys to memorize. Now, if you look at this, it doesn't seem like there's enough information because we have the probability of A union B as 0.75. We also have the probability of B as 0.4, but we're missing the probability of A, which is what we're trying to find, but we're also missing the probability of A intersecting B. But we have something at our disposal. What would you guys say if I told you we could say the probability of A equals X, probability of A is equal to some number X. Now keep in mind, X is a probability, so we know that that probability has to lie somewhere between 0 and 1. Remember, that's what probabilities do. It's either 0 being never happens and 1 being it always happens. So I'm going to make that equal to X. But now we have something that we haven't used, which is the fact that A and B are independent events. That means that the probability of A intersecting B is equal to the probability of A times the probability of B. This is good for us. Again, this only works with independent events. I don't know the probability of A, but I did say that that was X. And I do know the probability of B, which is 0.4. So what I'm going to do now is I'm just going to go to this equation and I'm going to replace the probability of A intersecting B with 0.4x, which comes from that formula. So this is that multiplication property. So really there are three main formulas we have. We have this formula in red, we have the conditional probability, and now we have our third formula, which is this over here on the right, which only occurs when you have independent events. And now this just turned into a pretty simple algebra problem. You've got X and negative 0.4x, which are like terms, so we know that's 0.6x. And if I subtract 0.4 from both sides, I get, if I could actually do some math here, gives you 0.35 is equal to that. And then this is where you guys can do a little bit of calculator work and do both sides divided by 0.6. And I think I have a calculator on mine. You won't be able to see it, but I'll do it here. So we're doing 0.35 divided by 0.6. And our answer is 0.583 repeating. And if you want to do them as fractions, you can do that as well, but I'm not going to mess with that. So what did we just find? We just found the probability of A. So the probability of A is equal to 0.583 repeating. So that's part A. I know it's getting a little messy here. Part B now asks, what's the probability of A intersecting B complement? Now this is also one where you can utilize the fact that if A and B are independent events, then you can use some of the formulas we've already done. So if A and B are independent, use this formula up here, but we can tweak it a little bit and we can say, well, the probability of A intersecting B complement is equal to the probability of A times the probability of B complement. Again, this is the multiplication property. If A and B are independent, then A and B prime are independent. So the probability of A intersecting B complement is just equal to probability of A, which we just found to be 0.583 repeating, times the probability of B complement, which if B is 0.4, then that means B complement is 0.6. And there is your answer. So you do our previous, and again, I'm going to my calculator, and I got an answer of 0.35. So the probability of A intersecting B complement is equal to 0.35. Now, if you want, you can draw a Venn diagram for this one, but this is a type of problem where you can do it with straight equations, and I don't think a Venn diagram really adds much to it. Okay, that is it for the lesson. Your homework is posted in Teams. I will also send it through Remind, and that is section 6K. There are 5 problems. Again, I will post it on Teams and I'll send it through Remind. And if you guys have any questions, please let me know. Otherwise, this is the lesson for Thursday and Friday, February 3rd and 4th. I will talk to you guys later.